Okay, good day. Uh, for today, our discussion is about the solution of oblique triangles. Okay, here in our discussion, we'll focus on the solution of oblique triangles, specifically with the laws of sines and cosines. In addition, we'll also have the area of a triangle together with the Heron's formula. So first off, before we proceed with our discussion, the fundamental properties of triangle. Let's recall this first. Okay, so we all know that the sum of the angles in a triangle is always 180 degrees. So angle A plus angle B plus angle C is always equal to 180 degrees. In addition, let's review the triangle inequality theorem, wherein the sum of the length of any two sides of a triangle is greater than the length of the third side. Okay, so we have here A is less than the sum of B and C, B is less than the sum of A and C, and C is less than the sum of A and B. Okay, in addition, with the solution of oblique triangles, we have different cases to consider. So we have here, we need to recall the idea of the determination of a triangle when it comes to its three sides, two sides and the included angle, and then lastly the two internal angles and the included side. Okay, so we will use also the concepts in geometry to answer the problems here in trigonometry. So before we proceed with our formal discussion in solution of oblique triangles, let's derive first the law of sines and cosines. Okay, so it's important for you as an educator to know the formula. Okay, so where it started and how to derive it. Okay, so first off with the laws of sines, we have here two figures of oblique triangles. So as we all know, when it comes to oblique triangles, uh, those are triangles with no angles of right. Okay, no right angles. And here in figure 1.1, both angle A and B are acute angle. In figure 2, angle B here is an obtuse angle. Okay, so uh, in order to derive the formula of the law of sines, we need to draw a uh, perpendicular to AB. Okay, so let's say CD, okay, is perpendicular to AB here, so it forms a right angle. Same with the figure 1.2. Let's extend the side AB, and it is perpendicular to CD. Okay, so here we denote that its length is the height. Okay, let's represent that as h. Okay, and we form here a right angle. Okay, so since we have now a right triangle in this figure, we can apply the trigonometric ratios here. Okay, so first off, on both figures, in triangle ACD of this figure, triangle ACD, and this triangle ACD, we can have the trig ratio of the sine A. Okay, the sine A here is its opposite, which is uh, H. Okay, and then its hypotenuse, which is B. Same with this figure number 2. We have our opposite, which is H, and our hypotenuse is B. Okay, or we can say, we can derive this, we can cross multiply and obtain the value of H, which is B sine A. Okay, also, in both right triangle BCD, and here BCD, we can have again another relation when it comes to the sine B. Okay, so sine B here is h over a. So here, triangle BCD, our opposite here is h, and then the hypotenuse is a. Here, in triangle BCD, the opposite here is h, and the hypotenuse here is 8. Okay, so we can cross multiply this and we'll obtain the value of h, which is a sine b. Okay, so now in addition, let's have this figure 1.2. Let's focus here in figure 1.2. In figure 1.2, we have here the sine angle DBC. Okay, so here, this one, we can say that its value is h over a. Okay, or we can say this one, this angle, as since they are supplementary, we can say that this angle is 180 degrees minus b. Okay, which is both as h over a, its value. Okay, so now here, uh, let's use the concept, or let's use the identity of the difference of the sign. Okay, if you will recall the sin cos cosine, we can apply this in sine 180 degrees minus b. So that is sine 180 degrees cosine b minus cosine 180 degrees sine b. Okay, then let's evaluate. Sine 180 degrees is equal to 0, and cosine 180 degrees is equal to negative 1. And simplifying this, we can obtain, here this is 0. So negative times negative, that's positive. So sine b. So sine 180 degrees minus b is equal to sine b. Okay, so then we can say that the h here is equal to a sine 180 degrees minus b is the same as a sine b. Thus, in both figures, we can say that b is equal to sine a, b sine a is equal to a sine b. Okay, so from this, since they both are equal to h, okay, so we can equate them. B sine a is equal to a sine b. Or, if we divide both sides by AB, we can obtain sine A over A is equal to sine B over B. Or, if we divide it both sides by sine A sine B, we can obtain A over sine A is equal to B over sine B. Okay, so in a similar manner, we can draw a perpendicular from B to AC. Okay, so to have the another trigonometric ratios that we can obtain from this figure. So let's focus in figure 1.1. So again, from B, it's perpendicular to AC. Okay, and it forms a right angle, obviously. Okay, so from this, we can have, again, the trigonometric ratios. Okay, so again, the length of the BD here is H. So in right triangle ABD, here, triangle ABD, let's identify the trig ratio sine A. Okay, so here in sine A, its opposite is H, and its hypotenuse is C. Okay, or can cross multiply, we can obtain H is equal to C sine A. And then for the triangle CBD, we can have here the sine C. Okay, where sine C is equal to H over A. Its opposite is H, and its hypotenuse is A. Okay, or we can have here H is equal to A sine C. In the same manner, from the previous solution, we can equate this two, and we can have C sine A is equal to A sine C. So if we divide both sides by AC, we can obtain sine A over A is equal to sine C over C. Or, if we divide both sides by sine A sine C, we can obtain A over sine A is equal to C over sine C. Okay, since sine A over A is equal to sine C over C, and from our previous slide, we identified that sine A over A is equal to sine B over B. There, we can say that sine A over A is equal to sine B over B is equal to sine C over C. Or, A over sine A is equal to B over sine B is equal to C over sine C, which is the formula for the law of sines. So in any triangle ABC, the ratio of a side and the sine of the opposite angle is a constant. Okay, so from this two figures, we obtain the law of sines. In addition, let's have the law of cosines. So what about the law of cosines? So let's have the same figure. Okay, figure 1.1 and the figure 1.2. Okay, so notice here, in either right triangle ACD of the both figures, we can have b squared is equal to a squared plus ab squared. Okay, so here we have the b squared, our hypotenuse, is equal to h squared, which is this, the length of CD, and then the length of AD, which is AD squared. Okay, since we don't know that its value, so that's AD squared. Okay, same with this figure 1.2. In triangle ACD, and we can have this Pythagorean theorem, b squared, which is equal to h squared plus ad squared. Okay, while in the triangle BCD, for the figure 1.1, here in triangle BCD, we can have the sine B. Okay, we can obtain the sine B and the cosine B. So in this case, we have the sine B as opposite, which is h, and then its hypotenuse, which is a. And then for the cosine b, okay, which is the adjacent, okay, and our adjacent here is db, okay, since we don't know its value, or there's no representation, so let's represent that as db. And then its hypotenuse, which is a. So we have here the sine b and the cosine b. Okay, so let's cross multiply this, and we can have here the value of h, which is a sine b, and then for the db, that is a cosine b. So from this, let's try to manipulate here from the AD, okay, the relation of AD to this side. Okay, so then we can say that AD, this one, is equal to the difference of the length of AB and the length of BD. Okay, so from this, let's try to substitute the values that we obtain to this equation. Okay, in both triangles, b squared is equal to h squared plus ad squared. So if we substitute the values that we obtain, we'll have the b squared is equal to a sine b squared plus, here, ab minus bd is c minus a cosine b. So as you can see here, this length of AB is C, okay, the side C, minus the value of BD or DB, which is A cosine B. So that's why we have here C minus A cosine B. And we will substitute that value of AD to this one. Okay, so C minus A cosine B squared. Okay, then let's simplify this. So we'll obtain here b squared is equal to a squared sine squared b plus c squared minus 2ac cosine b plus a squared cosine squared b. Okay, so from this we have a squared sine squared b, and then here we have the c squared minus 2ac cosine b plus the a squared cosine squared b. Okay, notice that we have a common monomial factor for these two terms, which is a squared. So let's factor out that a squared. And we'll have the sine squared b plus cosine squared b. Okay, and we know for the Pythagorean identity that sine squared b plus cosine squared b is just equal to 1. As we simplify this, we'll have a squared plus c squared minus 2ac cosine b. Okay, which is equal to b squared. Okay, so now, let's try to manipulate in figure 1.2. Okay, in figure 1.2, we have here the sine angle CBD, this one, is equal to h over a. And its cosine CBD is equal to the length of BD, okay, the adjacent, and the hypotenuse, which is a. Okay, and then let's manipulate that. Cross multiply, we'll have a is equal to a sine angle CBD, and BD is equal to a cosine angle CBD. Okay, and we know earlier that angle CBD is the same as the supplementary. Okay, so that is 180 degrees minus B for this angle. Okay, and if we will use again the difference identity for the sine, we can evaluate this sine 180 degrees minus B as just sine B. Okay, and then for this one, cosine 180 degrees minus B is the same as negative cosine B. So use the sine and cosine identity difference. So with that, we'll obtain a sine B here, and here dB is equal to negative a cosine B. Okay, so again, cosine 180 degrees minus B is the same as negative cosine B. Now, so from the previous slide, we identified in right triangle ACD, we have b squared is equal to h squared plus ad squared. So from that, let's try to obtain the values of the AD. So here in this figure 1.2, AD, the length of the AD is equal to the sum of the length of AB and BD. Okay, the length of AB here is C. Okay, and the length of BD here, as we identified earlier, it is negative A cosine B. So if we substitute that, we'll obtain C minus A cosine B. Okay, then if we will substitute that to our equation, we'll obtain B squared is equal to A sine B, which is our H, plus C minus cosine B squared, which is the same from our previous solution in figure 1.1. And we'll obtain B squared is equal to A squared plus C squared minus 2AC cosine B. So from that, we obtain the law of cosines. So the remaining equation may be obtained by the cyclic changes of the letters, so that you can obtain the other form, such as this one, the a squared is equal to b squared plus c squared minus 2bc cosine a, and then c squared is equal to a squared plus b squared minus 2ab cosine c. So in any triangle ABC, the square of any side is equal to the sum of the squares of the other two sides diminished by twice the product of the sides and the cosine of the included angle.